How you doing, guys? Welcome back to another Medic Mind GAMSAT video. My name is Harry, and today we're going to be looking at the Section 3 GAMSAT topic of motion and forces. So a couple of objectives that we want to try and complete today. First of all, we want to develop an approach. We want to have an idea as to how, when we look at motion and forces, what are the typical questions we might come across and how can we tackle those? Now, motion and forces is such a broad topic that is very difficult to have a single approach, but it's more about just understanding the basic level at each kind of subtopic and then from there being able to tackle the questions. It's not really about having a singular approach, but really having an overarching understanding of the different topics involved in motion and forces. Secondly, with that comes familiarizing yourself with equations. Often with motion and forces, the best way to learn it is to not necessarily mindlessly learn off equations, but to be honest, just learning off the different relationships between parameters, and that'll really give you a good understanding of how different things relate to each other. It's a lot easier than just learning, for example, a definition, in words of something. Learning an equation helps you understand how things interact with each other. And that's especially important when you're thinking about physical concepts. Finally, we're going to deal with sample questions, and primarily we're going to deal with questions here. We're going to look at particularly some graphical questions that will help give you an idea as to why it's important to have a fundamental understanding of the physical ideas, because they can be applied to questions that aren't as straightforward as they might first appear. So how do I approach motion forces? Well, you really need to be familiar with a lot of topics. Now, this is really going to be very much an overview and to kind of outline some basic ideas and definitions that you really need to go over. But if you want to understand the topic kind of in a more broad sense, you're going to need more information than just this video. But this video is going to be a really good start for you to give you a little snippet as to what's important in each of the topics that come in motion and forces, which is an incredibly fundamental topic to physics and really to a lot of the questions you're going to see in Section 3 physics in general. So becoming familiar with equations is really important. Becoming familiar with the different parameters, the units involved. These are kind of things that are going to come up regardless of what you see in physics. And so this topic is really fundamental and actually hopefully a topic that you're coming across pretty early in your studies of physics, because it's going to encompass a lot of things that you're going to come back around to in some of the other topics in physics. So firstly, mass. So mass, weight, and center of mass. You need to be able to understand mass. Mass is a quantitative measure of something called inertia, right? So if we have a force applied, what resistance do we have to its change in speed? And we see a lot of that kind of stuff coming up in some of Newton's laws, for example. Also understanding, what is, when we think of mass or do we think of weight? Do we understand how to convert between them? Do we understand that, when we're dealing with weight, weight is the pull on gravity, right? Is how much pull we have on gravity, whereas mass is, how much matter there actually is there. And so understanding just at a basic level what mass is, really important, something you might come up for you in some questions. Newton's first law. So we're going to have a quick talk about some of the Newtonian laws. Of course, you're going to see them a lot across all of physics. They're so fundamental and really important. And the first law is essentially that a body will remain at rest or in a constant state of velocity unless a force acts upon it. And this is a really basic idea that we will see in everyday life, right? The idea that, for example, if there were no air resistance or friction when you were driving a car and there was nothing opposing it from moving, then if you drove it at a particular speed without accelerating, it would move with that same speed until eventually something acts on it, right? Be that a brake, or in our case in a real world, that is air resistance, that is friction, okay? So a basic thing, but it'll come up a lot when you're dealing with maybe if you're dealing with projectiles or you're dealing with multiple bodies in motion and how they interact. Newton's second law. Newton's second law, you may have come across this before. This is the idea that F is equal to ma. It's a very famous equation. It's an equation that you should have right there in your head if you don't already. It's a very simple equation to learn. It's simply a proportionality between the force experienced by an object is proportional to its mass times its acceleration. And again, those are just important ideas to understand. Those vector values are really important to understand. Again, when you're dealing with motion and different forces being applied, you have to understand that each individual object is consistent with the second law of motion. Third law, we've probably all come across this law in day-to-day life, and it's the idea that for every action, there is an equal and opposite reaction. So for example, I'm sitting at my desk here, and so I am applying a force downward towards the floor. The floor is applying an equal and opposite force upwards back to me, and that's why I am static in this position. I'm not falling beneath the floor, and I'm not being pushed up to the ceiling. Again, a relatively simple concept, but something you're going to come across again and again, and these fundamental ideas are important to kind of understanding more complex ideas in physics, so just have that in your head. Newton's law of gravitation. Gravitation, really, really important. So there's an equation that's F is equal to G times the two masses that might be interacting, divided by the square of the radius between them. And the idea here is that Earth, for example, exerts a force on matter that is proportional to the mass of that matter. And so it's really just an idea that, for example, if we think about the acceleration due to gravity, it's again, if we ignore air resistance, we're talking about how, if something weighs more, that if it's got a greater mass, then there will be a larger attractive force, and how those are involved. And you might see some questions come up in, for example, some questions to do with kind of different orbitals in space, and you might have distances that you're given between them. And so understanding Newton's law of gravitation, really, really important. The gravitational constant, just have a basic idea of what those values are, really important when it comes to motion and forces. So right angles, right? So when we think about right angles, I guess often you'll see this come up in questions related to, for example, work done, right? So if you're talking about circular motion and the direction of a force here, is the direction first in circular motion is perpendicular, is actually perpendicular to the direction of motion, right? So the essentially the force changes the direction. So what happens is, if you're actually at a right angle, in theory, you're tangential to a circle, right? That force that's being applied is constantly perpendicular to your direction of motion, and that's why you get circular motion. So right angles come up a lot, and even more simpler than circular motion, you may see different, for example, addition of vectors. So that's another really basic idea. For example, you might have come across vectors either pointing, a vector pointing this way, a vector pointing this way, and you actually want to go top to tail, right, when you're adding those, and that's some basic kind of Pythagoras kind of maths. So if you have two vectors here, what's the resultant vector? So understanding right angles for that purpose can be important as well. Freefall motion. If you haven't come across the SUVAT or UVAST equations, then I would recommend having a look at those. Those equations kind of pertain to the different kind of values that allow you to assess, for example, a projectile or a body that is moving. And again, we're talking about motion and forces, so this is really important. So for example, U denotes the initial velocity of a projectile, V denotes the final velocity, and then A denotes the acceleration, and then T denotes the time that you might be starting at, and S might be the distance that it has traveled at a given time, right? So what's really important is that between those five values, you can actually learn a lot about moving objects, particularly if you have three of those values given. So UVAST equations, if you haven't seen them before, there are a number of equations that pertain to kind of free fall comes under that, but also projectile motion. And that leads me into the next topic here, as you can see, which is projectile motion itself, right? So incorporating those UVAST equations, if you haven't come across them, we get things like the time of flight, which we can look at, right? How long a projectile in motion is actually, moving, and how far it travels. So what's its initial velocity? What's its horizontal displacement? How far does it move? We can look at the S there of our UVAST. And time of flight is really important, as I said. And you might look at the vertical velocity as well, of course, right? If a body moves from this position to this position, right? If you think of it as, American football, for example, right? The quarterback throws the ball and it goes in a sort of a kind of parabolic arch. And so it starts here. How high does it go? At what point have I reached my maximum height? And so there are a lot of things in physics that are really useful to know. And one of them is projectile motion and free fall motion, and they all tie into the U-VAST equation. So if you don't understand those equations, those are really high yield. So translational motion. So really this kind of again ties in with the other things I've talked about so far, but it's the idea, particularly in 2D, but also when you're dealing with coordinates or something like that, it's the idea that we can shift positions, right? Bodies shift position. And that can come in a number of different areas. You might even see it, for example, in you might be dealing with things to do with work done, right? You might be dealing with planes. And an object is moved from here to here, and you might be working at the work done, but then they might also ask you coordinates and how something is moved, the path that it took to get there, or things like that. So important to understand translation motion. It's quite a basic topic, really. Friction, we've all come across this. I mentioned it earlier on. It's really just talking about the idea of sort of resistance to relative motion. It's an opposition force, really. So, when we're dealing with surfaces and we allow for friction, we have to understand that this force will oppose the movement of something. So particularly, we'll see that in inclined planes. So you'll see where an object, for example, might be moving, right? And one of the opposing forces that that stops it, for example, if we think of Newton's law, that an object will continue to move unless an opposing force acts on it, right? Well, in this case, friction is acting on it, right? So it is not just going to perpetually move. That is one of the forces that it's going to stop it. There are other at play, but physics is but friction is one of them, an important thing to understand. Next thing is inclined planes. So this kind of comes into it as well, where I talk about this. And if you don't understand your cosines, your sines, then, and your kind of angular mathematics, really useful to understand for inclined planes when you're dealing with different forces. For example, you'll have a normal force. If you have a plane, right, you'll have a force that acts kind of along the plane or perpendicularly to the plane. You'll have a force that acts along the plane. You'll have a normal force to the plane, and you'll have a friction force. So you have a lot of different forces moving in different directions, moving a body in different directions on an inclined plane. So really important that to understand things like sine, cosine, and how the mass and gravitational force, so force due to acceleration due to gravity, how all of these come together. And that's where inclined planes are going to bring in things like your mass. Your classic ones would be mass times acceleration due to gravity, and the cosine of theta, which might be, for example, the angle of the inclined plane. So if you don't understand those little ideas, go back over them. Really important to understand. Circular motion and centripetal force. So this is something that I spoke a little bit about earlier on when I was talking about little kind of directional forces, if you will, or right angles. So when you talk about circular motion, it's the idea that we have a force that's acting perpendicularly to a circle, and because this force acts tangentially, we constantly are the force is acting and actually resulting in a change in direction, right? Because we are connected to, for example, what's happening is, if this force is somehow connected to the center of a kind of circle, if you will, then what happens is this force acts to continually change the direction, and what we actually get is an inward force, which is called the centripetal force. And that's why if we swing something around, we actually have a force acting inward that is holding that piece in place, right? So the force on the perpendicular force is moving its direction, but there's also a force inward, and that force is the centripetal force. And you would see that, for example, if you're driving around a roundabout, you would be experiencing something called centripetal force. Hooke's law. So Hooke's law pertains to springs. You will definitely see this come up in places. It's in a basic concept again, but an important one to understand. You might see it as F is equal to minus kx, where F is the spring force, K is the spring constant, and X would be the displacement of the spring from its original length. And the idea is that forces can extend and compress a spring, right, by that distance X. And you'd also be looking at, for example, restoring forces, right? But it's important to understand, particularly with springs, that what is the restoring force of a spring, and how much, for example, if I stretch how much beyond a certain length can I stretch a spring with which I can restore it completely. And so those things come up a little bit. It's just important to understand that basic idea of F is equal to minus kx. As I say, the spring constant, it's a really, really small thing to cover, but definitely something you should look at. Tension. So this kind of ties in with the next thing that I'm going to talk about, but it's talking about so pulling forces, right? We know about tension, right? If we there are many instances where you will deal with that kind of force, right? If you, for example, if you hold something from a string and you put a weight at the bottom of that, right, we're creating a tension force, right? And this is really important for the next thing that I'm going to talk about, which is pulley systems. So pulley systems are just really important because they apply Newton's second law in particular. But the idea is, if you have, for example, you will see a lot of questions where they relate, for example, two masses, and there might be a pulley at the edge of a table, and you'll have two masses. And basically we've got one acting down here, but right, so we've one mass hanging from a string that's acting downward, but then we also have a weight on the side which is kind of opposing it, but also you've got a friction force there as well, which is kind of holding that. And so what's important is you can actually work out the tension force between these two and what what tension on the string these forces are creating. So a tension force is really, is not as kind of intuitive as the others as far as equations are concerned. So definitely something to look at and understand it in terms of particularly Newton's second law, as I said. So I have gone through a lot there already, just even summarizing. And as you can see, we're already into a lot of time into this video. And I just want to say that, look, there is a lot to cover there, right? Huge topic. It consists of loads of different subtopics. And the idea is that I've introduced you to concepts there. Take each of those concepts, take time to understand them and, review them in whatever way helps you. Once you've done that, if you're comfortable with that material, that's great. And the questions we're going to cover, you're going to find very, very straightforward. And in fact, I think you should have a look at these questions anyway and see where you're at. Some of these concepts you may never come across directly, but the kind of the theory behind them is fundamental to physics. And that's what's important. It's not about learning a lot of things off that are not intuitive. It's actually the opposite. It's about learning things off that actually, when you understand them, are quite intuitive, and they will help you with not getting confused by physical mathematics that really tie into each other topic to topic. So this is a really good foundation for you. So, it's important to memorize equations. Now, within reason, when I say memorizing equations, it's not like every equation you come across, you should learn it. It's just when I talk about a lot of the topics I've spoken about there, for example, the basic ones, right? You'll see some others come up in physics, but, force is equal to mass times acceleration, or some stuff to do with, maybe inclined planes. If you understand your sines, your cosines, and their relationships, very basic mathematical stuff you've probably covered before. But it's important because using equations, you have to be comfortable, because you won't just be given an equation and given things to substitute in. You might need to rearrange an equation that you've seen before. You might be given an equation and you actually have to maneuver it. So if you're really comfortable with equations, it's useful in that respect. And also because then you will understand the concepts better. Okay, so now I'm going to cover a couple of questions. If at this point you want to cover some of the topics before you go to these questions, that's absolutely fine. You can pause the video. However, I'm going to cover these couple of 4 questions. I think it's worth it for you to have a go with them with me, and then we'll take it from there. So the first question says, look at the velocity and acceleration portions of the graph, which we can see in the bottom 2 graphs there. Which of the following best describes the relationship between the components of motion? So when we're talking about motion and forces, this is a topic where you will see a lot of graphs, right? When you're dealing with projectiles or things like that, one of the best ways to represent kind of their motion or how they're acting in a given time period is graphically. So you will see that often. So get comfortable with graphs in this area. And so what is the relationship, right? So is there an inverse relationship between the components of motion? So between velocity and acceleration? Well, again, if you understand these topics, then you won't have an issue, right? Here's my acceleration graph. Here's my velocity graph. And actually, I can already tell straight away, is there a positive correlating relationship which is b, for example. Well, I mean, again, looking at the graph, I can already say that, you know, it's not necessarily correlating, right? Positive correlating relationship, should I say. Now, that means that when one goes up, the other would also go up, right? And that's not the case, right? We can see here, for example, that this velocity here is going up while acceleration is maintained at a particular given spot. So it's not going to be B. Is there an inverse relationship? Well, no, because when this is going up, this isn't going down. So immediately I can say, well, there's not an inverse relationship. And we should also understand, you know, how acceleration affects velocity, right? With a given change in velocity or a change in acceleration, that will affect your velocity, right? And if I change my velocity, I have done that by either accelerating or decelerating, right? That they're intrinsically related in that way. And so a change in velocity has a concurrent change in acceleration. Yeah, I'm happy with that. So let's have a look. And indeed, a change in velocity does have a concurrent change in acceleration. D, I actually hadn't looked at there. A velocity of 0, there's no acceleration. That's also not true. I should have clarified. That's an important thing to clarify, actually. But as you can see, at a velocity of 0, there's no acceleration. Well, that's not actually quite true, because when we start monitoring something, right, first of all, it doesn't have to start at 0, but in this case it does. However, at the moment you start looking at something, it can be starting to accelerate, because even at 0, acceleration has to occur at some point. And if it starts with a body at rest, it's still happening, even though at the instantaneous moment it starts, the velocity may well be 0. But an important thing to understand. So again, this tip is just, as I talked about, understanding graphs. It's incredibly important, and actually it'll really help you get a better grasp of certain physical concepts. But also you can see that not every question you're going to come across is going to deal with, you know, physical concepts exactly. It will incorporate them, but really it's just looking for you to observe the different things that have been given to you. Okay, so on to question 2. Now, with the last question, I realized I actually didn't give you a moment to pause the video to try the question. So what I'm going to do here is I'm going to give you a moment to tackle this question. Pause the video if you need, and we'll take this in a moment. Okay, so hopefully you've had a chance to tackle this question. The question is, what is occurring at a time of 10 seconds? Now, again, here we just need to know a couple of things. If I look at 10 seconds, what can I already interpret from this? Well, I can see at 10 seconds, first of all, acceleration is below 0. So that means I'm decelerating, right? So the minus sign particularly important there. Velocity, when it has a minus or a plus, the only thing I would say is it's not incredibly important, in the sense that you could be moving left or you could be moving right. And if you denote one as positive, the other would be negative, right? In other words, in 2D, I could be moving right or left, right? Or I could be moving, if I'm looking at it this way, I could be moving forward or backward. But, you know, in theory, the absolute value is relatively kind of more important, unless direction is a particular note. And obviously in velocity, you do have, it's different from speed in that it has a direction as well. But here, so decrease velocity. So we know we are decreasing velocity at 10 seconds, so that's fine. So we can omit C. We also know acceleration. Well, we know we're decelerating, so we're not accelerating. So that already gives us our answer, because 2 of these here say that we're accelerating. This one here says we're accelerating. This one here says we're accelerating, and we're not. So indeed, the answer is B. And also, if we were to look at the third thing, it says decreases meters per second of distance coverage. And that's also true, because at 10 seconds, you can see that the parabolic curve is actually beginning to taper off. And that means that, remember, if you're to draw little mini triangles here at a given speed, you can see that in this area of the graph here, we've got a steeper curve. So we've got a larger change in distance compared to here, where it's not as large. And therefore we are indeed decreasing the meters per second of distance coverage, you know, per unit time. We are effectively decreasing that that portion of the triangle, as you can see there. So important side note, but even then, if we knew the first 2 concepts, we'd covered our answer. So question 3, pause the video now and have a quick go at this question. Okay, so the question asks, what is occurring at a time of 25 seconds? So if we look at a time of 25 seconds, what can I see here? Well, again, I can see that even though we are moving in the negative direction for our particular purpose, we are increasing our velocity, right? If we pick a particular direction, although I said in theory, it's not important for your absolute velocity, it may be important in terms of stating whether you are increasing or decreasing velocity. So in this case, because our velocity is here and we're saying this is negative velocity, we are increasing effectively our velocity, even though effectively, because if I'm moving in this direction, and if we consider me moving to my right is positive, and we perceive moving to my left as negative, I might be moving this way because I'm going negative, but I'm actually slowing down. But I'm actually increasing my velocity, even though I'm slowing down, because of the direction I've chosen as positive and negative. So that is where the positive-negative relationship does become important. So I am increasing my velocity. I am also at 25 seconds accelerating. We know that. We can see that here. Now, cessation of journey, we know it's not A because I'm not ceasing the journey. Why is that? Because at 25 seconds, you can see there is a remainder of the journey left. And that's an important thing to point out. When you monitor something, if you're monitoring something in motion, for example, often, and you would see that in the lab as well if you're ever dealing with physical concepts, I can monitor something and in its beginning, it's not moving, and then it accelerates. And you might see that, a flat line to begin with, and then something accelerates. So the cessation of the journey is the moment when you have stopped, right? You have fully stopped. And even if you were to consider that as not moving anywhere, now, that may not be sufficient, but we can also see that the journey hasn't ended because, we haven't finished out the time that we've monitored here. And that's why the journey isn't over. If we monitor for 30 seconds, then even if it stopped moving, the journey isn't ended because something can happen in theory. So indeed, we finally know that there is a plateau of distance coverage is reached. Now that is true because we can see here, we've reached a plateau. So we know that we're happy enough that it's C. Also, one thing I noted that these were similar answers. This says increased velocity, acceleration, plateau of distance coverage is reached. So this actually technically implies that there's an increased plateau of distance coverage reached. They're very similar answers. The question arguably is not phrased the best, but sometimes you'll get that in GAMSAT and you have to be prepared. So in that case, it's more appropriate that C is there. B isn't quite phrased in the correct way that you would hope. And indeed, we're correct. We have an increased velocity, we are accelerating, and there is a plateau of distance coverage reached. So we've covered what's going on in all three graphs, and we're happy enough. Again, graphs, these last two questions, you need to read directly off the graph. Be comfortable looking at a graph and trying to interpret it, even if it's information, even if the block of information beforehand isn't something you've seen before. Just be comfortable with graphical analysis. It's a skill that can be applied universally, so get used to it. Okay, the last question. Have a go at this question, pause the video, and we'll try it in a moment. So, when is the greatest speed? Now, this is an interesting question. So technically, the greatest speed would be at the highest velocity. Now, when does that happen? So your greatest speed is as I say, it's technically when you've got your highest velocity, if you will, and also a slope on the distance time graph would be quite high at that point. In other words, there are a couple of things that we can note. Firstly, when the slope, so if I actually use a blue here, when the slope of the distance time is particularly steep, that's an important thing to note. So when the slope is particularly steep, we are clearly changing our velocity significantly because the amount of distance that we are covering in a particular time is significantly higher. Now, the other thing to note, as I say, is that some of the others incorporate areas where we don't have the greatest speed. So for example, 15 to 20 seconds. Well, if we look at that area is here. I would say, is that the greatest speed? Well, no, it's not. And also the other thing to note is that, again, when we deal with speed is technically your distance divided by your time. So really, I don't even need to look at the velocity graph, but the velocity graph can help me out, but I don't need it. Importantly, as I say, it's the highest slopes, right? It's the most significant slope. So there are interpretations here, but the best interpretation is that you have 0 to 4 seconds, contains your steepest slope, or your greatest speed, right? Your quickest change, instantaneous change in the distance time graph. So we have high speed, right? A steep slope. And also, again, remember that we're dealing with the absolute values, so that could be positive or negative, which is why we've got two sets there, 0 to 4 and 23 to 27, because your speed could be in either direction. But remember, speed doesn't have direction, so you can't say that the negative isn't the greatest speed. Okay, it doesn't have a direction, so the sign wouldn't be important if it came into effect anyway, just because it's a negative slope. So let's have a look at this. Indeed, it is 0 to 4 seconds and 23 to 27. So again, your interpretation and understanding of, if you're looking at a speed, are you looking at velocity, are you looking at acceleration, how all three of them tie together. This is actually quite a generous graph because it's put one on top of the other and made it very easy for you to interpret. There's no guarantee that GAMSAT will put in a graph that is actually set up in that way. They might make it a little more difficult. For example, if I had those graphs side by side, it wouldn't be so easy to interpret this, and I really have to think about it a little more, because them being on top of each other, you can see the dotted lines here make it very easy to interpret these side by side. So your take-home points, right? There is so much there, and I will be the first to admit that this is a big topic. I'm someone who studied my undergrad in physics, so I was very comfortable with this area, but I realized that for people who haven't been introduced to much physics, this is a big challenge. So revise the theory. Anything you are uncomfortable with that I have mentioned or covered today, that is something that is going to be fundamental to your understanding of physics, and it is worth taking the time just to have a look at it. It's not about memorizing everything you see. People that take the GAMSAT will know that. It's more about just having an understanding of things. And from there, then, if you tackle a question and it comes up again in the GAMSAT, at least you have that initial familiarity and you know that you've understood a concept once. You don't have to have learned everything off. However, that brings me into point number 2 for your take home, which is memorize some of the equations. And it's for the purpose of understanding the relationship between ideas, right? You're going to come across equations. You're going to come across things where you have to change units, right? You have to manipulate equations to find the right parameter that you want to isolate. And so the more comfortable you are with certain equations, the better it is. Also, for certain things that, for example, I always talk about things if there are proportionalities involved, or if things relate to each other, like distance, distance time graphs, how or velocity time graph, or acceleration. How do different things relate? It will help you to learn equations to establish those relationships and to make it easier. I don't have to think about what a kind of English definition of something is if I understand what the equation is, because that will help me deal with that. And particularly with physics, when you're dealing with graphs or equations or mathematics, it's not so important to have all the English in your head, and more important to have the kind of parameters and their abbreviations understood. And finally, practice as many questions as possible. We've only tackled 4 here. There are plenty to move you on. Look at graphical analysis is really important, and really just try and get an overview of all of these topics, and you are really well set with a foundation to further your knowledge in the area of physics and to really improve your score here. So that's the lesson complete, guys. Thank you so much for joining me. I hope this has been really helpful for you, and I look forward to seeing you again in another video. Thanks a million. See you soon.